Hello everyone, my name is Denis. I'm a compiler engineer at Intel, and today I would like to talk about why we should become good at optimizing our code. Okay, so this is essentially the goal for my talk. Okay, so I will explain why performance, is ever more important, and how you should prepare yourself for the future that's coming. So, we live in an increasingly data-centric world, and we generate just enormous amount of data every day, right? So, in all this, growing amount of data, it actually fuels the need for faster computations, right? But unfortunately, the modern CPUs, are not enjoying that the same speed up as it used to, during the past decades, right? So on this chart, you can clearly see that the trend for single-threaded performance, right? It's essentially slowing down, right? The growth is slowing down. So it used to be the case that some software vendors, so they actually relied on hardware for providing speed ups for their application, right? And they did not spend the human resources or developer resources themselves to improve their code. Instead, they just simply relied on hardware for providing that speed ups, right? But unfortunately, the easy ride for them is over, right? So we all must start optimizing our code. We must start paying more attention of how our code is actually running. And this is essentially what John Hennessy said in his Google I/O talk, which was titled "The Future of Computing," where he said that the general purpose computing is dead, and it is time for specialized hardware. And the same vision is actually shared in another popular paper, which is called "There is Plenty of Room at the Top." This is a recent paper by 2020, published in 2020, and they try to identify the key areas that will drive performance gains in the nearest future. Okay, so and they identified the three areas: software, algorithms, and hardware architecture. Okay, so the hardware architecture, is so they envisioned the future where the hardware architecture will be will be streamlined. Okay, so and there will be specialized hardware for every workload. So, and this hardware will be designed to do just this task and nothing else. Okay, and this is the trend, not just the future but already a present. Okay, and we see this already in our lives, right? We have a whole bunch of accelerators. We have the graphics accelerators, we have the FPGAs and the ASICs and DSPs. We have the chips for visual processing. We have the specialized chips for neural networks and all this stuff, right? And even even the tiny devices like this earphone, for example, right? In the future, or maybe even today, there will be a dedicated streaming chip inside the earphone that will be just designed for doing noise canceling and nothing else. Okay. The second area, it is algorithms. Okay, so and well, you might be surprised, like, well, what's new in algorithms, right? Well, it turns out that still new algorithms are being invented. For example, the machine learning is the area where the research is quite active. So the new algorithms are still being invented there. And then the second and interesting thing is actually the AI can also discover new algorithms. And there was I remember there was an early evidence that that AI discovered some new algorithm, and this is because the AI doesn't have the human bias, the bias that the humans have, right? So and the AI explores the entire computational space, right? While people tend to reject crazy ideas, and this is the opportunity for the AI algorithms to find the new approaches, right, to existing problems. So, and then the third area is software performance engineering or software tuning, and this is actually the area where we as developers can make an impact. Okay. So what do I mean by that? It is, it is the tailoring your software to the specific hardware that is, that is used to run your application. Okay. So this is essentially the low-level tuning. This is the way how we can extract performance in the future, okay, from our programs. During the post-more era, it will become ever more important to make code run fast, and in particular to tailor it to the hardware on which it runs. Okay, this is again from the same paper. There is plenty of room at the top. And also in this paper, the author actually presented the interesting table. This is the table that shows the results of performance engineering of the naive matrix multiply kernel written in Python. Okay, by performing the number of transformations and optimizations, they were able to speed up this naive matrix multiplication code by more than 62,000 times. Okay, this is just enormous, right? A huge improvement. So, but the reason why I show this slide is not to pick on Python. Okay, Python is a great language. I write Python myself. But the reason why I'm showing this table is, is to break beliefs that all the hardware, all the software is optimal by default, okay, which is simply not true, right? And those are two examples what do I mean about, by software tuning, okay, by tailoring your code to specific hardware, okay. Those are the kind of transformations where you utilize specific hardware features, okay, to improve performance of your code. But you might be asking, well, isn't it the solved problem? Like why do I have to care about performance anymore, right? Why do CPUs do not solve all of those problems, right? Why compilers aren't they designed for for optimizing my software? Well, it turns out that those components have their own limitations, right? So, for example, CPU is great at crunching numbers, so it does so, at incredible speed. Unfortunately, the CPUs cannot, magically optimize your badly written code. Okay, so for example, if you wrote the bubble sort, the CPU cannot, magically, run the quicksort in the background. Okay, so and then compilers, right? Compilers are great at eliminating unnecessary work. However, when it comes to more complicated decisions, they usually tend to rely on their cost models and a bunch of heuristics, which are not perfect and do not generate the optimal code for every program in the world, right? So the point of my talk today is we must become good at optimizing our code. Okay, there is no free lunch. The free lunch is over, and those are just a few examples from the giants. Why performance tuning, the even 5%, will yield the drastic impact. Can make a drastic impact on some companies. So, what can you do to prepare yourself for the future? First of all, learn your technology stack. Okay, learn the hardware internals on which you are running. Okay, learn the CPU microarchitecture. Learn to read and understand the basic assembly instructions. Okay. If your program spawn in lots of processes, learn about the OS scheduling mechanisms, learn about the priorities, about the affinities, how you can pin the threads, and then learn about compiler optimizations and options that are available to you. The trend in today's world is actually that we as a developers we unfortunately are getting more abstracted away from the real hardware. So it creates some barriers, right? Why? Well, because there is a bunch of layers between us, between the application layer and the actual hardware. Okay, so there is, you know, there is operating system, there is compilers, there is libraries and frameworks. Nowadays there is, you know, a whole bunch of orchestration and virtualization layers, right? So it is, you know, it is becoming a little bit more difficult, you know, to tune our code for the specific hardware, since you know, it can be the case that when we run our software in the cloud, we have no idea on which CPU it will be running on, right? Then avoid performance traps, right? So well, and the number one, you know, trap is to make predictions about performance. Okay, the modern systems are so complicated that it is essentially impossible to predict how your code will perform on a modern hardware. Okay, so do not try to guess, always measure. Then the second trap is to make changes with no impact, right? So I see, you know, I see people sometimes make you know, changes like they change I++ to ++I, and they hope that, you know, and then they hope that they will get, like, you know, huge performance improvement from this change, right? Unfortunately, most of the time it's just a wash, right? So do not rely on your intuition when you make changes in your code when you try to improve it, but always rely on careful performance analysis, right? So this should be the driving force for your optimization work. Then the next trap is, you know, people optimize their programs while they do not know their data. Okay, so and they end up optimizing their program for some theoretical use case which is not practical at all, right? Another trap is to create a bad benchmark, right? So when they write the benchmark, for example, it's easy to, you know, to write the benchmark and think that it is really measures the code that you wrote, but well, in fact, it can measure something else. Okay, so it is really easy to get fooled with, you know, with a badly written benchmark, or again, again, people sometimes write the misrepresentative benchmark, right? Again, the benchmark which does not represent the practical workload, right? So the workload that people will be running, right, in the real world. Then the fifth trap actually is funny. So do not blindly rely on big O notation. Okay, do not discard the hardware effects. So just to give you an example, because of the hardware effects, the insertion sort outperforms the quick sort on a small arrays. Okay, so do not just, you know, go with whatever algorithm is optimal in terms of big O notation. Always, you know, think about how CPU friendly or, you know, or hardware friendly this algorithm and data structure is. Okay, so the second example is, you know, is binary search. Binary search is a great algorithm. Unfortunately, it's absolutely horrible for CPU. Okay, it experiences the high number of branch mispredictions and cache misses at the same time. Okay, well, why? Because in this algorithm, right, you jump either to left or right, but there is a 50% chance of going left or right. So this is essentially, like, you know, the worst case for the CPU branch predictor. And then every time you jump to a new location, right, this is pretty much a guaranteed cache miss. So and this is actually the reason why we have, you know, the specialized memory layouts just for, you know, for improving the binary search, like, for example, the Eitzinger layout. So then learn to find the bottlenecks, right, and learn to discover optimization opportunities. So there is a number of performance approaches that you can follow, right? There is no one right approach that you should always use, right? But all of the approaches have one thing in common. Okay, they all based on first collecting some data and then interpreting this data, right? So for example, code instrumentation, right? We all have done this in the past, right? You probably remember, like, you know, inserting the printf function in a printf in the beginning of the function just to count how many times this function was called, right? Then the flame graphs. Flame graphs are the popular way to visualize the hotspots in your program. Then compiler optimization reports, right? So compiler has, have this special report where it can, which will allow you to track what optimizations compiler did for some particular piece of code. And then there are some CPU specific or some hardware specific analysis, like for example TMA. TMA is a top-down methodology analysis which allows you to identify the bottleneck on the CPU level, right, and locate the exact place in the code where it happened, where it's happening. Okay, the example can be you can track down the source code, the line in the source code where you experiences the most number of cache misses or branch mispredictions. Then this is the roofline. There is a roofline analysis, roofline performance model, which allows you to assess the performance of your program relative to the theoretical maximum capabilities of your machine. Okay, it also allows you to, and it also guides your optimization process. So then, once you learn to identify the bottlenecks, it is actually only a half of the job, right? So the second half of the job is actually to fix the issue, right? To fix this, to fix the issue, right? You should know what options are available to you. And there is some this list on this slide. This is not an exhaustive list, of course, but just to give you an idea, right? You can employ the PGO, which is Profile Guided Optimizations. This is essentially like a free speed up. You should try it. Then there is vectorization, memory prefetching, optimize. You can optimize the layout of your program. You can search opportunities for improvement in function inline, and you can optimize memory accesses. You can perform some loop optimizations. You can apply domain specific techniques like cache warming, like cache allocation. You can try to eliminate branch mispredictions and so on and so forth, right? And then practice. Okay, practice using tools, right? Practice using tools that are available on your platform. If you are on Linux, try using perf and strace for tracing the system calls, right? Learn using the great products like vTune Profiler and Intel Advisor, right? And then just practice, right? Just pick some benchmark and play with it, right? Try to improve its performance, right? See how you can do this. Try different performance, approaches, right? Try instrument your code. Try to trace system calls. Try to find the hotspots in the program, and so on. So on my blog, I actually I organize the performance challenges. So this is essentially the practice step. So people so I give the people I give the benchmark to the people, and they try to optimize it. So this is some of the there are some of the examples that we were able to to achieve. So together all the participants were able to speed up the 7-zip benchmarks by 12%. They were able to optimize the Lua interpreter by 5% and Canny Edge image detection algorithm by more than 2x. Okay, so the takeaways: software doesn't have optimal performance by default. Okay, but unfortunately the hardware is not growing. The hardware performance is not growing as fast as it used to during the past decades, right? This is why performance tuning will be one of the key drivers in the nearest future. So, and how you can prepare yourself, right? So learn your technology stack, right? Learn CPU microarchitecture, read assembly code, learn about the OS internals, right? Learn how to how to work and with compiler, and avoid performance traps. Like always measure, do not rely on your intuition, but rely on careful performance analysis instead. and then practice practice optimizing some existing benchmark or your application. And this is it from me today. Thank you very much for listening. If you have questions, this is the right time to ask. So here is how you can find me on the web. So I'm available on Twitter and LinkedIn, and here is my blog, which is easyperf.net. And yes, I wrote a book about performance analysis and tuning on modern CPUs. So the PDF version is available for downloading for free. And yes, thank you very much for attention.
Thank you, Denis.
Hello. Hello.
And we're live. Okay. How is Santa Clara?
Yeah, thanks. Yeah, everything is good.
Okay. I think we lost your video again.
Oh, really? How about now?
You're back.
Can you see me now?
Yes, everything's fine. So,
Yep.
thank you for the really great talk. I couldn't stop. I was looking at the free lunch is over message, and it took me back to probably 10 years ago or 20 years ago, when people were thinking there is a conspiracy between Microsoft and Intel to make Windows more and more expensive so that Intel can sell more processors. So
Yeah.
I'm curious, do you think the industry actually gets your message that the free lunch is over and we have to start to be much more efficient in the way we write software?
I think actually, I think actually people are, pretty much separated in how they view whether, the Moore's law is over or not. So I think like, most of the people tend to think that, that the free lunch is over and and there is the time, for specialized hardware and share, let's say, my point of view. So there are still people that try to defend Moore's law and and try to break down and try to get some design wins in physics and try to try to prove and try to find maybe some opportunities in improving tech process and so on and so forth. But unfortunately the Dinard scaling is pretty strong, right? So it says that as you shrink the size of your transistor, the leakage current gets higher. So essentially, so the more you shrink the size of your transistors, the more heat emission, right, there is, right? So it gets warmer, and essentially you will hit the limit. So there are a number of tricks people do still to make the Moore's law go longer, but well, I don't know.
Yeah, and I think especially in a world where everything becomes elastic, right? More and more of the workloads happen in cloud, where more servers or CPUs get added on the fly. I think normal engineers don't get to think about lunches over that often.
Maybe, yeah, and actually, so I like what you just said, right? So I think our world is becoming more heterogeneous, right? And this is actually already a present, not a future. It's happening right now today, right? We have we have a whole bunch of red accelerators, and we actually, so maybe the second point of my talk, which I was not discussing, but still, right? So we must be prepared to program the heterogeneous hardware. Okay, if you will, right? So, and this is challenging, right? Well, why? Because it's not easy, right, from a programmer's perspective to to write some code that will be run efficiently on all hardware in the world, right? So this is actually the hard task, and well, right, and the example of this might be in the past, developers were writing for example software like games, right? The games for one GPU, let's say NVIDIA,
and then what they did, they actually just ported the same game to the AMD, for example, hardware, right? So I think we don't want to be in this kind of world in the future, right? So we need some way to efficiently program heterogeneous hardware in the future.
I think that's probably worth the whole conference in itself, because one way I can think of that happening is to say the hardware builders have to kind of abstract the differences to us and provide a pre-optimized but the same API set to all the higher level engineers. But I think then, to your point about games, you'll never get the same level of optimizations that you could get if you get close to the metal.
Right. Yeah. Yeah. So this is challenging, yeah, and there are trade-offs, right? So trade-offs between between how easy it will be to program versus how closer to the metal you will be, and how you will be able to extract the most amount of performance from the hardware. So.
And something else, I actually noticed a tweet yesterday about, you mentioned it as well in the talk, the performance optimization challenges. And I think that's really a cool idea, because I think lots of young engineering talent spends time in the CTF, capture the flag hacking competitions, because they try to solve hard problems, but those are usually offensive hacking problems. So I think it's great to manage to find an outlet, capture that creative energy, and put it into solving performance issues. Do you see a lot of, what's your experience? Do you see a lot of attendance? Are people excited?
Well, actually, in terms of attendance, well, not much. So I started those challenges about 2 years ago, but then I had a long break because of my book, because I was writing my book. So well, in terms of attendance, I think each of the edition of my challenges, attracted around 10 people on average. So not much, of course. But yeah. So right now it was just so I started it just to prove an idea, like and to see if it will be interesting to the people, right? So at the time it's not automated. I just do this in my mailing list, right? So everything is pretty much ad hoc. Well, yeah.
If I can suggest something, and if you want, we can even follow up offline afterwards. Maybe do a partnership with some of the bigger CTF organizations, because they have hundreds, if not thousands, of people for the weekend trying to figure out challenges, and they can turn it into a hacking event, saying your code has to be more optimal than X in order to break to this gate and get whatever flag hides behind the gate, right? So maybe doing a partnership with the CTF organizers might be a way to bring this kind of forums to the world. I think it's a super creative idea.
Yeah, thanks. Thanks. Yeah, so I started it as a practice, right, for people to being able to practice those low-level optimizations, right, of what I was talking about, right? So the CPU level optimizations. And I think there is, well, at least I haven't found any of such such challenges elsewhere, right? Because, well, there's a whole bunch of practicing you can make on the data algorithms and data structures and algorithms front, right? So there's a whole bunch of websites, but you cannot any pretty much practice the low-level tuning.
Yeah, it's super exciting. I would really love to talk to you more about it. We can take it offline. I think there's potential for fun things to do together.
Sure. Yeah. Absolutely.
All right.